next program is about numbers and sequences. Hello, I'm here to help you and our puzzling pupil make the most of what you know when you come to do your Key Stage 2 maths tests in May. In each of these programs, and in our books, audio tapes and on the internet, we're looking at the maths you might find tricky. This time, it's about numbers and number sequences. In the test paper, there are often questions like this.
Here is a number sequence. Write the missing number. Then there's a 1, a 3, a 6 and a 10 and a box to write the next number in the sequence.
To help answer this problem, you need to work out some kind of rule about what's being done to each number in the sequence to turn it into the next one. Now, once you've cracked the code and worked out the rule, you can apply it to the last number of the sequence, and that will give you the missing number at the end. Let's try an easier one first. How about this number sequence? What could you do to 1 to get 2, the next number in the sequence? Add 1. Yes, though you could also multiply by 2. So we can't be sure what the rule is yet. Look at the next step in the sequence. What do you do to 2 to get 3? Well, it isn't multiply by 2, it's add 1 again. And so it is for the next step from 3 to 4. So we've cracked the code. Now we're sure about our rule, it's add 1, we can apply it to the last number, the 4, to get the missing number. 4 add 1 is 5. So the missing number is 5. Number sequences in the test are usually a bit more tricky than this, and the rule you're looking for may be a bit more complicated. So let's get back to your question.
OK, I've got to find some rule that applies to each of these numbers to give me the next one in the sequence. Well, to get from 1 to 3, I can add 2. But if I look at the next step and add 2 to 3, I don't get 6. So adding 2 can't be the rule. But what else can it be?
Well, don't give up. What is the next step?
From 3 to 6 is either times 2 or add 3. So that doesn't give me a rule either.
Well, then try the next step. That might settle it.
OK, to get from 6 to 10, I add 4.
So what's the rule for this number sequence?
Oh, I see. It's add 2, then 3, then 4. The number I add increases by 1 each time.
You've cracked the code. Well, now you've worked out the rule, apply it to the last number.
If I have to increase what I add by 1 each time, then the next step will be add 5. 10 add 5 is 15, so the missing number is 15.
So write it in the box for 1 mark. Now, don't forget there's another part to this question. It asks you to explain how you worked it out.
Oh, so I write in that the amount I added on each time went up by 1.
There are often questions like this, where the answer is a word or a sentence instead of a number. There's a special name for this sequence of numbers. They're called triangular numbers, and this is why. Each of these numbers can be made into a triangle shape. Start with 1, then 3, then 6, then 10, then 15. Here's another special sequence of numbers. They're called square numbers. This is why. Each of these numbers can be made into a square shape. Start with 1, then 4, then 9, then 16, then 25. And you get a square number when you multiply a number by itself. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. And so on.
Here's another question with the number sequence. It says, Megan makes a sequence of numbers starting with 100. She subtracts 45 each time. Write the next two numbers in the sequence. And they give 100, 55, 10 and 2 boxes. With this one, they tell us what rule to apply.
Yes, but there's something to watch out for here.
Right. 100 minus 45 is 55, and 55 minus 45 is 10. So 10 minus 45 is, oh, I've got to be careful here, we're going into negative numbers.
Well spotted. Let's hold it there and look at an easier number sequence with some negative numbers, like this. The rule is that we're subtracting 2 each time, which is fairly simple until we get to the number 1. Then what happens when we subtract 2? Subtract 2 from 1 is 0 minus 1. So the first missing number is minus 1. And if you subtract another 2, minus 2 minus 3. So minus 3 is the next missing number. Does that help?
Okay, so 10 minus 45 is minus 35, and minus another 45 is minus 80.
Another 2 marks. When we talk about numbers, there are some special words worth remembering. An even number is divisible by 2. An odd number isn't. A prime number is a number that is only divisible by itself and 1. Let's spot a few prime numbers. Now 1 doesn't count as a prime number, so what's next? 2. Can it be divided by another number? No, so it's a prime number. 3. No, so it's a prime number. 4. Well, 4 divides by 2, so it's not a prime number. 5. A prime number. 6. Divides by 2 and 3, not a prime number. 7. A prime number. 8 divides by 2 and 4, not a prime number. 9 divides by 3, so not a prime number. 10 divides by 2 and 5, not a prime number. 11, a prime number, and so on. To check if a number is a prime number, it's useful to know some shortcuts to whether a number is divisible and by what.
A number is divisible by 2 if the last digit is even. A number is divisible by 3 if the sum of all the digits is divisible by 3.
A number is divisible by 5 when the last digit is 0 or 5.
A number is divisible by 9 if the sum of all the digits is divisible by 9. A number is divisible by 10 if it ends in a naught.
Once you've got your divisibility rules sorted out, you can tackle 2 other useful words: multiples and factors, and the difference between them. A multiple is what you get when you multiply numbers together. We say that 10 is a multiple of 5 because you can multiply 5 by 2 and get 10. We can also say that 10 is a multiple of 2 because you can multiply 2 by 5 to get 10. So 10 is a multiple of both 5 and 2. A factor is a number you can divide exactly into another number. 5 is a factor of 10 because you can divide 5 into 10. 2 is a factor of 10 because you can divide 2 into 10. 5 and 2 are both factors of 10. Let's try to break down 12 into its factors. What divides into 12? 1 and 12. 2 and 6. Anything else? 3 and 4.
Here's a question about multiples. It says, Millie and Ryan play a number game. What's my number? Is it under 20? Yes. Is it a multiple of 3? Yes. Is it a multiple of 5? Yes.
Well, have a go.
Multiples of 5 are 5, 10, 15, 20, but it has to be less than 20. That leaves 5, 10 and 15. But the number has to be a multiple of 3, and 3 only goes into 15, so the number must be 15.
So write it in the box. A formula is some maths where the numbers are replaced by letters. Look at this missing number question. It says 60 take away something equals 26. We could write that as 60 minus some number equals 26. It would be shorter to write 60 minus n instead of some number. Or we could write 60 minus y equals 26. The maths would be exactly the same. Can you work out what y is?
Well, if the difference between 60 and y is 26, then y is the difference between 26 and 60, which is 34.
Right. There's a reason for using a formula and having letters instead of numbers in your maths. It's when you don't know what the numbers are, but you do know the relationship between things. Look at this question.
There are 12 pencils in a box. A school buys 24 boxes. How many pencils does the school buy?
In our program on problem solving, we worked out that if there are 12 pencils in one box, then in 24 boxes, there are 24 times 12 pencils altogether. The total number of pencils is the number of pencils in one box multiplied by the number of boxes. Now that's true however many pencils there are in each box and however many boxes. So we can write a formula that will work for any number of pencils and boxes, and that is T for total pencils equals P for the number of pencils in each box times N, the number of boxes. And so we don't confuse the multiplication sign with an X, we write it as T equals Pn.
Here's a question that asks for a formula. It says, to print a book, it costs 3 pence per page and 75 pence for the cover. Write a formula for the total cost of printing a book with a cover. If T stands for the total cost in pence and N is the number of pages.
Off you go then.
Well, if each page costs 3 pence and there are N pages in the book, then the cost of the pages is 3 times N. Then I need to add the cost of the cover, that's 75 pence. So the total cost in pence, that's T, equals 3N plus 75.
In the box it goes. That's the end of our program on numbers and number sequences. So let's check what we've done. We looked first at number sequences and saw how you have to spot the mathematical rule that applies to each step of the sequence, and then how to use it to get the missing number. We looked at special numbers like odd and even, prime numbers and squares, as well as multiples and factors. Finally, we saw how you can create a formula by replacing numbers with letters. If you want to, you can go over all this by winding the tape back and looking at bits of the programme again. And there are also books, an audio tape, and our interactive Revise Wise website to help you prepare for your tests. The next programme is about interpreting data. In these programmes, and in our books, audio tapes and on the internet, we're helping you with the things you might find tricky in your Key Stage 2 maths tests. This time, it's how to interpret data. Now, what do we mean by that? Well, in the test, there are lots of questions that give you data, or information, in different ways, and you have to interpret it. That is, to work it out and explain what it's telling you. Here's a question where they give you a table of figures about the cost of stamps, and you have to work out how much it costs to send a letter. This one has a bar graph showing you the number of people who went into different shops. This is a graph of someone's temperature when they were ill in hospital. One thing they all have in common is that they each tell a story, and you have to work out what it is.
Here's a question with a table of figures. Can you help me with it?
OK, what does it show?
Well, it's a table of the number of stamps used each day in school. Then it has the days of the week and the prices of the stamps.
Let's have a good look at that table and see what it's telling us. To start with, it's got a title, and that tells you what the table is about. That's the number of stamps used each day in the school. Then it shows you the two things that the table is comparing, the days of the week across the top and the price of the different stamps down the side. So, for example, this row across tells you how many 30p stamps were used on each day of the week. 6 on Monday, none on Tuesday, 2 on Wednesday, 8 on Thursday and 4 on Friday. This column downwards tells you how many stamps were used on Thursday. 32 19p stamps, 6 25p stamps, 8 30p stamps, 1 35p stamp and 12 50p stamps. So what does the question ask?
Well, it asks how many 25p stamps did the school use on Wednesday. So if I go down the column for Wednesday and across the row for 25p, then the answer is where the two meet. That's 4.
Well done. Write it in the box and get a mark. Tables are a popular way of showing information. You see them everywhere, and they all tell you different things. Here's a table showing different mobile phone tariffs. Here's a Football League table with the teams listed down one side. This is a bus timetable with the places it stops down the side and all the times going across. Even the TV listings are in a table with all the different channels across the top and the times down the side. When you're preparing for your test, have a look at some tables like these to get the hang of how they work and the information they're giving you. Bar graphs are another way of showing information.
There's a bar graph in this question. It's about how much money some children collected.
Let's have a good look at that bar graph. Like a table, it has a title that tells you what the bar graph is showing you. That's the amount of money they have raised so far. Then it shows you the two things that the graph is comparing. The names of the children up the side, that's the vertical axis, and the amount of money in pounds that each of them has raised along the bottom. That's the horizontal axis. Another thing to watch out for is what each division along the horizontal axis is worth. That's the scale. In this case, 1 division equals £1. This bar, for example, tells you how much money Hassan raised. To find out the exact amount, you go from the end of the bar to the amount in pounds axis. And there you can read the figure 5, which means £5. So what does the question ask you?
It wants to know how much money the children raised altogether. So if I look at each bar in turn, I can see how much money each child raised and then add it all up. So Louise raised £3. Hassan raised £5. David raised £4. Sarah raised £7. And Donna raised £6. So that's 1, 10, 10, 5. That's £25 altogether.
Now on that bar graph, each division along the horizontal axis was exactly £1, so it wasn't difficult to work out the value of each bar. It's not always that easy.
This is a bar chart. It shows you how many cars are sold over a period of 8 months. The month that sold the most cars was the 8th, and they sold just under 80 cars.
Notice how the length of the tallest bar didn't exactly line up with a numbered division on the axis, so Emma had to estimate that the amount was just under 80 cars. You often have to look carefully at the numbers on a bar graph, because very few have one division on the graph worth exactly 1 unit of measurement. In this bar graph, the numbers on the vertical axis go 0, 4, 8, 12. So each division is worth 4 people. To find out what the post office bar is worth, the line you take across ends up halfway between 20 and 24, which must be 22.
Here's another bar graph, and this one's got centimetres along the bottom that go 0, 25, 50 and so on. So each division here is worth 25 centimetres.
Can you answer the question that goes with it?
Well, it says, Sue jumped 212 centimetres. Draw Sue's long jump on the graph. So I'm looking for 212 centimetres along this axis. But it isn't there.
Then you have to work it out from the numbers that are there.
Oh, I see. 212 is about halfway between 200 and 225. So I'll make a mark there and draw the bar like this.
Bar graphs are a useful way of showing information, and when you're preparing for your test, look out for them and work out what they're telling you. Here's a bar graph showing the money people in different countries spend on their gardens. This shows the sale of musical instruments and how much people spend on different kinds of music. You can even make bar graphs of your own on a computer from information you've collected in a spreadsheet or database. Line graphs tell a story too. Over to the maths team.
This is a Weight Watcher graph. It shows that a person weighed 90 kilograms before they started the Weight Watchers course. During the course of 24 weeks, they lost weight, but in the last 4 weeks, they gained weight.
Graph questions in the test are often about working out the story behind the graph. Try that one.
Well, it's about Gavin, who is ill, and this is his temperature chart.
And what can you tell by looking at it?
Well, it starts on the 5th of March when his temperature is low, and then his temperature gets higher until the 10th of March. And then it comes down again and levels off by the 15th and 16th of March.
Well, that sounds like the story behind the graph, but what does the question ask you about it?
It says, estimate Gavin's highest temperature, shown on the graph. Give your answer to one decimal place. OK, so the highest temperature will be where the graph is at its peak. That's here.
Yes, but what's his actual temperature?
Oh, I run along the line to the temperature axis and read off what it says. That's... Oh, it's not by a number. It's in between 38 and 40.
But the question does say that you have to estimate.
So this division between 38 and 40 must be 39. And my line is just a bit higher than that, so I guess it's somewhere around 39.1 or 39.2.
Well, that looks just about right to me. This is a different kind of line graph. Along the horizontal axis are pounds, and at the vertical axis are dollars. Let's say that £10 are worth $15, so I can put a point on my graph here. I also know that no dollars equals no pounds, so I can put another point on my graph here. Now, if I join my 2 points together, I get a straight line which tells me the relationship between pounds and dollars. Now we've got the graph, we can use it to convert any number of dollars to pounds, or the other way round. Over to the maths team.
This is a conversion graph showing how to change pounds into dollars. To find out how many dollars are in £6, I will go across to the 6, get a ruler and go up to the line and mark out, and then I'll do the same again, go across onto the other axis, and it would be $9.
There's one more type of chart you might come across in your test, and that's a pie chart. You can guess why it's called that because it's circular like a pie, with the different amounts shown as different sized sections of the pie. The maths team explains.
This is a pie chart. It shows you how many hours of the day were spent on a particular task. I can see that about a quarter of the day was spent working and a quarter of the day was spent playing. About a third of the day was spent sleeping and about an eighth of the day altogether was spent on travelling and eating.
Look out for pie charts and investigate what they mean. This one shows how much of these different fish dishes were eaten in this restaurant. These two pie charts show how people spend their money on their gardens. You can make pie charts of your own on a computer. That's the end of our programme on interpreting data. So let's just check what we've done. We looked at tables of figures and how to read information from their rows and columns. We looked at bar graphs and saw that they have horizontal and vertical axes and a scale, and how to estimate the length of the bars. We saw how line graphs can tell a story and how to read them, and we used a straight line graph to convert from one thing to another. Finally, we saw that pie charts show information by the different sizes of their sections. If you want to, you can go over all this by winding the tape back and looking at bits of the programme again. And there are also books, an audio tape, and our interactive Revise Wise website to help you prepare for your tests. So, we'll let you get on with your test, and you get on with your television revision. The next program is about data handling. In this program, we're helping you with things you might find tricky in your Key Stage 2 maths tests. This time, it's data handling.
What do you mean by that?
Well, data is information, and in maths we usually get information as lots of numbers. Now here's a table of test scores for a group of 9 children. Now that list of numbers is difficult to make much sense of at a glance.
You could use them to plot a graph.
That's right. And this is the graph we'd get, which gives us a picture of the different marks people got. But there's more information we can get out of the numbers themselves. What if we wanted to compare these results with the following week's test, or with marks from another class? It would be really useful to have one number that gave an overall result of the whole class. Now this is where we need to use mode, median, and mean average. There are 3 different ways of getting an overall figure for this class's test results, and each way will tell us something different. The mode is the number that comes up most in a set of numbers. It's easier to work out what it is if you put all the numbers in order first, from the lowest to the highest. So, what number comes up most often? Well, there are 2 6s and 2 9s, but there are 3 4s. So 4 is the mode, the mark that most people got.
I can see how the mode can be useful to know, but what's the next way?
It's the median. The median is the middle value of a set of numbers. To find out what it is, first sort them in order, and then you can pick out the middle number. Now, there are 9 numbers altogether, so the middle value is the 5th one along, which is 6. So the median is 6, the middle test score that people got.
I can see that's a good measure of what the whole class scored.
Now, don't forget the third way, the mean average. Another way of getting an overall figure for the whole class is to add up everyone's marks and divide this total by the number of children in the class. The total of all the marks is 63, divided by 9, the number of children. That makes 7. So the mean average of this set of numbers is 7.
It's as if the children's marks have been shared out equally between them.
That's right.
I like that method. It seems the fairest way of measuring how the whole class got on in their tests.
But is it? Look at this.
On your marks.
Well, I think we have a replay of the race, Chris, and would you like to talk us through?
Well, I got a great start, and it didn't take me too long to get past Yusuf. And, really, by the time I handed over the baton, we was over 50 metres up.
We're with Holly Brook now.
Natalie, I understand, ran her personal best, but even with a good handover to Marcus, they were over 50 metres behind.
Holly Brook are well behind. Gemma, Marlborough's third leg, has already passed the baton to their final runner, and Kate has an impossible task making up the lost distance, and she's catching up. 30 metres to go, and Kate is closing on the red team, whose last leg is being run by 5-year-old Shakira Ekebusi, and it's going to be a photo finish. Quite remarkable. It's a dead heat. Let's have a look at the timings there with Brendan Foster.
Well, in the green, Yusuf started with 18 seconds. Natalie on the second leg ran 17 seconds. Then Marcus ran 100 metres in 16 seconds, with the last leg being run in 19 by Kate. 70 seconds to run 4 by 100 metres, an average of 17.5 seconds a leg.
Well, now let's take a look at the red team. Chris ran his leg in 11.5 seconds. Quite amazing timing. Followed by Barnaby, who ran in 15 seconds. Very good. Gemma ran the third leg in 17 seconds. In the final leg, Shakira, the up-and-coming 5-year-old from the Akabusi camp, took 26.5 seconds to finish the race. A total of 70 seconds for 4 by 100 metres.
Well, that's an average also of 17.5 seconds a leg, exactly the same as the green team.
The same mean average for two very different races. Let's go back to our test results. Say one pupil scored nothing in the test. What would the mean average be then? Add up all the scores, 54, and divide by the number of children, 9. That makes 6. So the mean average for this class has gone down from 7 to 6.
Oh, that isn't fair, because all the other children in the class did just as well. What happened to the median and mode?
Let's see. Sort the numbers into order first. The middle value is still 6, so the median is the same as it was before. And the score most people got, the mode, is still 4.
So maybe the mode and the median are fairest after all. The mean average can be misleading if one person gets a very different mark from the rest of the class.
That's right. One person getting 0 pulled the mean average for the class down 1 whole mark, but it didn't change the median or the mode.
Here's a question about mean and mode. It says, write a different number in each of these boxes so that the mean of the 3 numbers is 9.
OK, give it a go.
Well, if the mean of the 3 numbers is 9, then the total of those 3 numbers is 3 times 9. That's 27.
Good.
Now, I want 3 different numbers that add up to 27.
That's right.
Well, if I can't have 9, 9 and 9, I could have 8, 9 and 10. They add up to 27.
Certain, they definitely will happen, and they have a probability of 1. Along the probability scale between impossible and certain, we put events that are unlikely but possible, equally likely to happen or not, or very likely to happen. A fair coin has 2 faces, heads and tails. And when I toss a coin, there's an equal chance of it coming down heads or tails. And over several goes, I'll get heads half the time and tails half the time too. Now we can say the probability of getting heads is 1/2, and the probability of getting tails is 1/2. We can work this out mathematically. How many heads are there on the coin? 1. Divide that by the number of ways the coin could fall, heads or tails, that's 2. So the probability of getting heads is 1 divided by 2, and that's 1/2. And we can show that on the probability scale. A fair dice has 6 faces with 1 to 6 spots on them. And when I throw a dice, what is the probability of me getting, say, a 4? OK, let's work it out. How many 4s are there on the dice? 1. How many numbers are there on the dice altogether? 6. So the probability of throwing a 4 is 1 divided by 6, and that's 1/6. So, what's the probability of throwing an even number?
Well, I have to work out how many even numbers there are on the dice, and then divide it by the total number of ways the dice can come up. The even numbers are 2, 4 and 6, so there are 3 even numbers and 6 ways altogether the dice can fall. So the probability of an even number coming up is 3 divided by 6. That's 1/2.
That's right. Spinners are many-sided shapes like this, with each section numbered. This one has 6 sections numbered 1 to 6. If you spin it like this, it'll come to rest on one of the numbers. What is the probability of a number, say 3, coming up?
Well, there's 1 3 on the spinner, and there are 6 numbers altogether, so it'll be 1/6.
What about this spinner then? It's got 8 sides numbered 1 to 8. What's the probability of a 3 coming up now?
Well, there is still only 1 3 on the spinner, but now there are 8 numbers. So the probability must be 1 divided by 8. That's 1/8.
That's right. If you get a question about a spinner, check how many sides it's got, what numbers it has on it, and how big each section is. That's the end of our programme on data handling. So, what did we do? We learned that data handling means getting information from a set of numbers. The mode is the number that comes up most. The median is the middle value of a set of numbers. The mean average is the total of all the numbers divided by how many numbers there are. We looked at probability. How likely or unlikely is it that something will happen? We saw that the probability scale goes from 0 for events that are impossible to 1 for events that are certain. We saw how the probability of other events happening can be worked out as a fraction. If you want to, you can go over all this by winding the tape back and looking at bits of the programme again. And there are also books, an audio tape, and our interactive Revise Wise website to help you prepare for your tests. So, we'll let you get on with your test, and you get on with your television revision. The next programme is about measures. In this programme, to help you with your Key Stage 2 maths tests, we're looking at measures.
What do you mean by that?
Well, we use different units of measurement to measure different things. Like this. When you go shopping, you'll find that packets of solid things are marked in grams. Larger packs are marked in kilograms. Liquids are marked in litres. And some things are marked with their length or width in metres or millimetres. And all those quantities are measured in different ways. We measure small distances with a ruler. We measure longer distances with a tape measure. We measure even longer distances with a trundle wheel. Liquid capacity is measured in a measuring jug. And weight is measured on scales. All those ways of measuring have both large units and small units. In mass and weight, it's kilograms and grams. And it's important to know the relationship between them.
1 kilogram is the same as 1,000 grams.
1 kilogram, 1 gram. To convert from one to the other, you multiply or divide by 1,000. So if 1 kilogram equals 1,000 grams, 5 kilograms equals 5,000 grams. You multiply by 1,000. 500 grams equals 0.5 kilograms. You divide by 1,000. With capacity, it's litres and millilitres.
1 litre is equivalent to 1,000 millilitres.
1 litre, 1,000 millilitres, 1 millilitre. With distances, it's kilometres and metres.
1 kilometre is equivalent to 1,000 metres.
1 kilometre equals 1,000 metres. 4.5 kilometres equals 4,500 metres. Multiply by 1,000. 500 metres equals 0.5 kilometres. Divide by 1,000. For smaller distances and lengths, we use metres and millimetres. 1 metre equals 1,000 millimetres. There's another unit of length measurement you'll come across, the centimetre. And 1 metre equals 100 centimetres. 1 centimetre equals 10 millimetres. So to convert between these, you either multiply or divide by 10 or 100. There are often test questions about using different units of measurement to see if you know the relationship between them. Try that one.
Well, there's a picture of a model car and it says, the height of the model is 2.8 centimetres. The height of the real car is 50 times the height of the model. What is the height of the real car? That's easy. The real car will be 50 times 2.8, which is 140 centimetres.
But check exactly what the question is asking you.
Oh, it says give the answer in metres, so I have to change 140 centimetres into metres.
That's right.
Well, I know there are 100 centimetres in 1 metre, so 140 centimetres is 1.4 metres.
So write it in the box for 2 marks. So with problems involving measurement of distance, mass and capacity, watch out you give the answer in the correct units and know how to convert between them. Now look at the first part of that same question.
Well, there's a picture of the model car with a ruler underneath it, and it says, what is the length of the model? So what am I supposed to do?
Well, they want you to measure it. There are often questions like this to see if you can measure things accurately. So that's something worth practicing, like using a ruler. The maths team show us how to do it.
I got a ruler and turned it over to the millimetre side. Then I placed it up against the line exactly and measured along. It was 120, then I counted the millimetres on from it to the end of the line. And there were 7 of them, so altogether it was 127 millimetres long.
So the trick when reading a scale, like on a ruler, is to work out what the small divisions are that come between the numbered ones.
Well, if this is like a ruler, then I suppose the small divisions will be millimetres. So it's 8 centimetres and 5, 6, 7 millimetres.
Yeah, but check the question.
It says it wants the answer in centimetres to 1 decimal place. So 8 centimetres and 7 millimetres will be 8.7 centimetres.
Good. In the box. The other kind of measuring you may be asked to do in the test is to measure angles using an angle measurer. Over to the maths team.
I put the cross onto the point and make sure that the red arrow is level with the line. Then I move it down to the next line and it measures 60 degrees.
You try one.
Okay, there's a little drawing of an arrowhead and it says, below is part of a larger scale drawing of the arrowhead. The drawing has the same size angles as the design. Draw 2 more lines to complete the arrowhead accurately. Use an angle measurer, protractor. So they want me to make an angle of 40 degrees here and here. And it's telling me to use my angle measurer. So here we go. I put the centre hole of the angle measurer over the end of the line, line up the 0, then I turn the red line to 40 degrees and make a mark. Then I do the same on the other side.
And that's great for the angles, but don't forget they want you to complete the arrowhead.
So I need to draw 2 lines, like this. That looks okay.
Well done.
Here's a question about area and perimeter. Here, they want me to draw a shape which has an area of 10 square centimetres. And here, they want me to draw a rectangle which has a perimeter of 10 centimetres. Can you remind me of the difference?
Okay. The test often has questions about area and perimeter, so it's well worth getting it clear what they are. The perimeter is the distance all the way round the outside edge of a shape. The perimeter of this rectangle is the length of this side plus the length of this side, and this side. Area is the amount of surface a flat shape covers. The area of this rectangle is the length of this side multiplied by the length of this side. Now, does that help you with the question?
Well, in the first part, they want me to draw a shape with an area of 10 square centimetres. It doesn't say it has to be a rectangle. Now, each square in the grid is 1 centimetre square, so I need to count any 10 squares, like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
How about the next part of the question?
Right, they want a rectangle which has a perimeter of 10 centimetres. That's the distance around the outside of all 4 sides. The length of 2 sides will be half that, which is 5 centimetres. So to get the length of each side, I want 2 numbers that add up to 5.
That's exactly right. So what will they be?
Well, 3 and 2 add up to 5, so I can draw 2 sides here. One 3 centimetres and the other 2 centimetres. And another 2 sides of 3 centimetres and 2 centimetres here to make my rectangle.
You got it. Some questions about area are not so straightforward.
Here's another area question. It says, this plan of a garden is made up of rectangles and triangles. The area of each rectangle is 12 square metres. What is the area of the whole garden?
That's a good one. A shape like that, made from other shapes put together, is called a compound shape. To work out its area, you need to break it down into the simpler shapes that go to make it up. The maths team deal with a problem like that.
To find the area of this shape, I would split it up into 2 rectangles down there. Then I would find the area of one rectangle. There's 3 down that side, and there's 1, 2, 3, 5 that way. And I'd join them together, and that would make 15. Now I'd work on the second rectangle, and there's 3 that way, and then 5 down there as well. And then times them together, and that would make 15 as well. And then add the answers together. That would make 30 centimetres squared.
Does that help?
Yes. In this question, the shape is made up of rectangles and triangles. So I have to work out the area of each bit.
That's right.
Now, it tells me that the area of each rectangle is 12 square metres, and there are 1, 2, 3, 4, 5 of them. So the area of all the rectangles is 5 times 12, that's 60 square metres. Now, I know these triangle shapes are half the area of the rectangles, so that's 6 square metres, and there are 1, 2, 3, 4 of them, so that's 24 square metres of triangles. If I add the area of the rectangles and the area of the triangles, I'll get the area of the whole shape. That's 60 plus 24, 84 square metres altogether.
Good. So write the answer in the box. That's the end of our programme on measures. So, what did we do? We saw how different things have different units of measurement, and that there are different ways of measuring them. We looked at how to measure accurately using a straight scale, like a ruler, and how to measure angles with an angle measurer. We looked at area and perimeter, and how to work out the area of compound shapes. If you want to, you can go over all this by winding the tape back and looking at bits of the programme again. And there are also books, an audio tape, and our interactive Revise Wise website to help you prepare for your tests. So, we'll let you get on with your test, and you get on with your television revision. The next programme is about shapes. In this programme, to help you with your key Stage 2 maths tests, we're looking at shapes.
What sort of shapes?
All sorts of shapes. Now, most of the questions on shapes in the test paper are about knowing what they're called and how to describe them properly. Now, here they want you to draw a pentagon. Here they want you to pick out an octagon and a hexagon. Here they want you to say which of these shapes is an equilateral triangle and why. So, let's start by looking at some shapes that are two-dimensional. Two-dimensional shapes are flat. You can draw them on a piece of paper. Now, here are some 2D shapes. They've all got straight sides, and where the sides join, you get an angle. Any closed shape with straight sides that meet at an angle is called a polygon, which means many corners.
Well, that's not very useful, giving all those shapes the same name.
Well, hang on, each shape has its own name as well, and the name each of these shapes has depends on the number of sides and angles it has. Over to the maths team.
This shape is an octagon. It's an octagon because it has 8 sides.
This is a pentagon. It has got 5 sides. This shape is a quadrilateral because it has 4 sides.
You're more likely to come across the regular versions of two-dimensional shapes. Now that's when all their sides are equal and all their angles are equal too. Then they're called regular polygons. So a regular octagon has 8 equal sides and 8 equal angles. A regular heptagon has 7 equal sides and 7 equal angles. A regular hexagon has 6 equal sides and 6 equal angles. A regular pentagon has 5 equal sides and 5 equal angles. And a regular quadrilateral has 4 equal sides and 4 equal angles.
I recognise that. It's a square.
A square is another name for a regular quadrilateral, which has all its sides equal and all its angles equal.
And they're all right angles.
That's right. So you can call this shape a quadrilateral because it has 4 straight sides, a rectangle because its opposite sides are parallel and equal and it has 4 right angles, and it's a square because all its sides are equal and it has 4 right angles. Now, many shapes have more than one name. Over to the maths team.
This shape is a quadrilateral because it has 4 sides. It is also a parallelogram because both pairs of opposite sides are parallel.
This is a quadrilateral. It is a quadrilateral because it has 4 sides. It is also a rhombus because all the sides are equal.
Knowing the proper names of two-dimensional shapes and exactly how to describe them will be really useful to you in your test. A triangle has 3 sides and 3 angles where they meet. And there are different kinds of triangles, and you need to know something about them.
This is a triangle. It is also a right angle triangle because it has 1 right angle. This is a triangle because it has 3 sides. It is also an equilateral triangle because all the sides are equal and so are the angles.
An equilateral triangle has all 3 sides of equal length and all 3 angles equal too. An isosceles triangle has 2 equal sides and 2 of its angles are equal. A scalene triangle has none of its sides equal and all its angles are different. Now, in a right angle